All right, let's look at this example to see how these things play out. So it says compare the gravitational force for an object of mass m at sea level, the top of Mount Everest, and on the International Space Station. Assume the radius of the Earth is 6.371. The formatting was a little wonky here, so I wrote 10 to the third off here. Kilometers with a mass of 5.972 times 10 to the 24th kilograms. The height of Mount Everest is 8.849 kilometers, and the ISS is 400 kilometers from the surface of the Earth. So we're going to start with our equation, Fg equals g times mass of the Earth times mass of the object divided by the radius of the Earth squared. This is for sea level because the distance is function of the radius of the Earth. Now, we should be able to predict what we're going to get here, but let's do it out just to calculate and show. 6.3, sorry, it should be 6.671 for my radius of my, or sorry, for my gravitational constant. Make sure I get this written down properly. 6.673. 6.673 times 10 to the negative 11th kilograms meters, sorry, newtons meters per kilogram squared. Just getting back into the habit of remembering exactly what these are. Mass of the Earth is 5.972 times 10 to the 24th kilograms times mass m divided by 6.371 times 10, and it would be 10 to the third, but that's for kilometers. We want to make it times 1,000, so it's going to be 10 to the sixth, so it can be in terms of meters. And right here you can kind of see why you need to have absolutely massive objects, because this 10 to the negative 11th means anything that's not huge up here, we're just going to have a tiny number. So if I plug these in, again, in theory, you might have a prediction of what this equals. And if so, that's great. You can kind of double check, or you can plug things in and see if that's what we get. So 6.673 times 10 to the negative 11th times 5.972 times 10 to the 24th. Whoops. Backspace times 10 to the 24th divided by 6.371 times 10 to the 6th squared. And we'll know if we got this right. It does look correct. You end up getting 9.81 times m. And units should be newtons per meter. Newtons per kilogram. 9.81, which would also be meters per second squared. Because a newton per kilogram will be a kilogram meter per second squared, which is also the same as a meter per second squared times kilograms. Meters per second squared times mass m. And like I said, we should be able to predict this because this is exactly what we've been saying all along. If we're close to the surface of the Earth, we should see a gravitational acceleration of little g. So what I'm going to do, instead of calculating Fg for these other ones, I'm just going to calculate little g, because we know that the weight should end up, or the force should end up being m times g. So this is for Mount Everest. G is going to equal big G times the mass of the Earth times the radius of the Earth plus the height of Mount Everest squared, because that's how far you are now. So this will equal to 6.673 times 10 to the negative 11th newtons meters squared per kilogram squared times 5.972 times 10 to the 24th kilograms divided by 6.371 times 10 to the 6th plus 8.849 times 10 to the 3rd, because again we have to work in meters. And you can see that this 849, just at a glance here I want to point this out because this is the power of working in scientific notation. This is 1,000 times smaller than this number, which means we're changing the 1,000th place. We're changing this value right here. So you can kind of start to see how this shouldn't end up making a huge difference. But we'll pull that up just in case to prove that. So I'm going to come in here with my calculator, pull up the old equation, and then do plus 8.849 times 10 to the 3rd. And that will give us 9.79 m. Again, I'm going to put in that m again later, meters per second squared times m. I'll write that cleaner. So in other words, if you're on the top of Mount Everest, instead of the gravitational acceleration being 9.81, we're looking at closer to 9.79 meters per second squared m. So this is why, yes, even though it changes, we're talking about basically from the surface of the Earth to the highest point you can possibly go to on Earth. You're seeing this tiny, tiny change here. So now let's look at how much that matters on the ISS. G is equaling to, I'm going to just skip to the numbers and I'm going to kind of, skim through. Same sort of thing as before, just for saving time. 6.371 times 10 to the 6th meters plus, and now we're looking at 400 kilometers, so 400 times 10 to the 3rd meters, which you could also write as 4 times 10 to the 5th. And you can see, okay, this is starting to make a difference because now we're looking at 10 to the 5th, we'll be changing this 3 right here. But what you might find here might be interesting to some of you. Let me get the exact number for you. 400. You see that we get 8.69 meters per second squared times m, which, if you're curious, means on the ISS, the astronauts on the ISS weigh about 90% of what they weigh on Earth. So the gravitational pull is only reduced by about 10%. It's only about 10% smaller. And that'll lead into kind of some of the next lessons that we look at. So hopefully this showed some interest here.